Hi, I am Aravind Balaji, MS in Information Systems at Northeastern. This is my deep Q learning assignment for Info 7375. I built a TQN agent that learns to play Atari Ms Pac-Man using reinforcement learning. The agent starts knowing nothing and teaches itself to play through trial and error. I chose MS Pac-Man because it is a much harder reinforcement learning problem than typical choices like breakout or pong. It has 9 actions instead of 4, a complex maze with 4 ghosts, and a rich reward structure, pellets worth 10 points, power pellets worth 50, and cascading ghost bonuses from 200 up to 1600. Let me scroll to the environment analysis. So here is the environment analysis. The raw screen is 210 by 160 RGB. We process it to 84 by 84 grayscale and stack 4 frames so the agent can see which direction ghosts are moving. The 9 actions are no up, up, down, left, right, and 4 diagonals. The state space is 256 to the power of 28,000, way too large for a Q table. That is why we use a deep neural network with 1.7 million parameters to approximate the Q function. And here is the explanation of the states and the actions and the Q table size. This is the DQN implementation. The network has 3 convolutional layers that extract spatial features, walls, that is walls, ghosts, and pellets, followed by 2 connected layers that output 9 Q values, 1 per action. Next, the experience replay buffer stores 10,000 transitions. We randomly sample batches of 32 to break temporal correlations. Without this, the network would overfit to whatever part of the maze it's currently in. So this is the epsilon greedy policy. These are the exploration strategies. I implemented 3 exploration strategies. One is the epsilon greedy, the Boltzmann policy, and the UCB policy, which means the upper confidence bound. The epsilon greedy is the baseline, random with probability, epsilon greedy otherwise. Epsilon decays from 1.0 to 0.02. I also implemented Boltzmann softmax exploration and the upper confidence bound as mentioned earlier. And this is the TQN agent. So here we can see the baseline configuration. Before training, I ran a random agent for 20 episodes to establish a performance floor. You can see the random agent scores very poorly. It just wanders into ghosts and dies. This gives a reference point to measure how much the DQN actually learns. You can see it here. And these are the baseline hyperparameters. And here is the reward structure. And this is the baseline training. We can see that 60 episodes with epsilon greedy, learning rate is 1e minus 4 and gamma is 0.99. You can see the rewards increasing over episode as the agent learns to eat pellets and avoids ghosts. And the training plots shows rewards trending upward. episode length increasing, meaning the agent survives longer, loss converging, and epsilon decaying from 1.0 down to 0.02. The baseline achieved a mean reward of about 253, which is a significant improvement over the random agent. These are the Boltzmann equation parameters. I tested different values of alpha and gamma. When I increased the learning rate phi x to phi e minus 4, the training became unstable. The Q values oscillated and performance dropped. When I lowered it to 1e minus 5, learning was too slow to converge within the 60 episodes. For gamma, the results are dramatic. Reducing gamma from 0.99 to 0.90 made the agent short-sighted. It could eat nearby pellets but couldn't plan routes through the maze. The ghost eating cascade happens many steps after the power pellet decision, and with gamma 0.90, that future reward is discounted too heavily to influence the agent's behavior. Gamma 0.80 was even worse, essentially random navigation. Here we can see the uh, experiment comparison. For the exploration policy, Boltzmann softmax underperformed epsilon greedy. The reason is that early in training, the Q values are noisy garbage and Boltzmann trusts those noisy values when choosing actions. Epsilon greedy's uniform random exploration is actually more robust because it doesn't depend on Q value accuracy. For exploration parameters, the baseline with epsilon starting at 1.0 scored 253. Starting at 0.5 dropped to 132 because the replay buffer didn't get diverse experiences from the full maze. Slower decay dropped to 121 because the agent wasted time on random actions instead of exploiting what it learned. Here we can see the comparison. Here is the final comparison across all 8 experiments. The horizontal bars show mean reward, max reward, survival time, and percentage improvement over the random baseline. The baseline configuration alpha 1e minus 4, gamma being 0.99, epsilon greedy performed best overall. Every trained agent significantly outperforms random play, confirming that decoherent learning is working. The summary table ranks all experiments. The key takeaway is that gamma has the largest impact. Lowering it cripples the agent's ability to plan ahead in the maze. Q-learning is value-based, not policy-based. It learns the Q values, the expected future reward for each state action pair, and the policy is simply the argument max of those values. There is no separate policy network and no policy gradient computation. Comparing DQN to LLM roles, the DQN learns through millions of trials and errors frames from raw pixels, and LLM agent uses pre-trained knowledge and reasons in natural language. DQN is near optimal for one specific game. LLMs generalize across tasks but aren't as precise. The expected life the expected lifetime value in the Bellman equation is the total discounted future reward from a state onward. In MS Pac-Man, the value of moving toward a power pellet includes not just the plus 50 pellet reward, but the entire ghost eating cascade plus 200, 400, 800, 1600, and that follows. That's why gamma 0.99 is essential. For integrating DQN with LLMs, I propose a hierarchical architecture. An LLM acts as the high level planner, setting goals like clear the upper right quadrant, while the DQN handles real time joystick movements to achieve those goals. Here you can see the comparisons. The Q-Learning versus LLM-based agent comparison here. For code attribution, let's see the next section. The network architecture was adapted from PyTorch's reinforcement learning tutorial, adjusted for 9 actions with gradient clipping. Frame pre-processing uses Gymnasium's built-in wrappers. Everything else, training loop, 3 exploration policies, all 8 experiments, visualization, and all documentation is my original code. The project is MIT licensed, compatible with all dependencies. All 18 rubric questions are answered in line in this notebook, plus a separate documentation file with detailed written answers has also been submitted on Canvas. Thank you.